Welcome all to the award ceremony of the Graph Neural Networking Challenge 2021. So for this award ceremony, we will first start with a brief introduction in the problem statement, and then Albert Cabellos, who is the director of the Barcelona Neural Networking Center, will announce the awards of the challenge. Just afterwards, we will have presentations from top 5 teams. So you will have all the opportunity to make questions after each presentation. So please, I would like you to start very good discussions on these solutions. And finally, we will make a short closing of the ceremony. So starting with the introduction, I just would like to give you some overview on the Graph Neural Networking Challenge. So this competition is a series of annual challenges on graph neural networks applied to computer networks. And so far, we have celebrated 2 editions. And each edition brings a fundamental challenge on the application of graph neural networks to different networking problems. So this competition represents the first and the only challenge, or even nowadays, on the application of graph neural networks applied to computer networks. As you already know, this is organized as part of a broader competition, which is called the ITU AI/ML in 5G Challenge. So in this context, I would like to sincerely thank the ITU for their great support to organize this challenge, and especially to our colleagues at ITU, Thomas Vasicolo, Vishnu Ram, and Reinhard Skoll, because I think that it wouldn't be possible with their great support. So I think it's important to thank them in this context. Just to give you a broader overview, the ITU AI/ML in 5G Challenge has in this edition 14 different problem statements that are hosted by partners from the academia and industry. So the Graph Neural Networking Challenge is one problem statement that is hosted by the Barcelona Neural Networking Center. And this edition is sponsored by Shillings. So here you can see also the cash prizes of the grand challenge finale of the ITU AI/ML in 5G Challenge. Well, going back to the Graph Neural Networking Challenge, I would like to give a brief overview on the problem statement for this edition. So first of all, I would like to introduce the concept of the digital twin network. So in general, a digital twin is a virtual replica of a physical object or system. So a digital twin network is basically a virtual replica of a physical network infrastructure that enables to evaluate the performance of the network under certain what-if scenarios. So as an example, we could evaluate what would happen if I change some configuration of the network. So what would be the final performance without actually applying this configuration in the physical or in the real infrastructure, or what would happen in the event of a failure. So for building such a digital twin network with machine learning technologies, we should follow the pipeline that you can see here in this slide. So first of all, if we were a networking vendor, we should need a network testbed that is under controlled conditions, so that we can generate different samples. For example, injecting different traffic distributions, generating different congestion levels, testing different configurations. So after this extensive testing process, we can generate a data set. And this data set can be used to train a machine learning model. So after the training process, we would have the final digital twin product. And this digital twin product, as any networking product, should be ready for deployment directly in real networks in production. So in this context, we would first need a machine learning model that can generalize to other networks that were not seen during training. So after being trained with some samples of the networking testbed at the vendor's lab, this product or this final digital twin should be able to make accurate predictions and to operate correctly in the target real-world networks. So in this context, what we can see is that graph neural networks are a key enabler in this sense, as it is the only machine learning technique that demonstrated capability to generalize to different networks and configurations that were not seen during the training phase. But in this case, we still have a limitation. And the problem is that typically, the networking lab, we would have a network testbed of limited size. And then this digital twin should be deployed in real-world networks that are typically much larger in scale. So as a reference, we can expect that real-world networks can be more than 10 times larger than the vendor's training testbeds. And the main limitation of state-of-the-art GNN-based solutions for digital twins is that they don't scale well from the small-scale networks that can see during training to the large scale real world networks where they would be eventually deployed. So this is the main limitation of this edition of the challenge, which is entitled Creating a Scalable Machine Learning Based Digital Twin Network. And in this context, what we could see is that scalability is a general problem for graph neural networks. So if you check the literature of the machine learning field, you can see that this is not solved in general for any GNN model, except for some few recent proposals that are very specific to some problems like graph classification and other very specific use cases. But this is not solved for the construction of scalable GNN-based digital twin networks. So in the end, this is an open research problem. Well, it was an open research problem. I think that we will see very good solutions that already solve it after the celebration of this challenge. So particularly, in this edition, we asked participants to build a digital twin network that would be like the box that you can see here in this slide, and it should be fundamentally based on a neural network model. So the input of this solution is a network state snapshot or a network scenario that is particularly described by a network topology, a traffic matrix, and a routing configuration. And this digital twin network should reproduce the input network scenario and produce predictions on the per path mean delay. So we will evaluate, or we evaluated, sorry, the accuracy on delay predictions of this model. And as this edition is focused on testing the scalability of the proposed solutions, what we did was to provide participants a training dataset that contained a wide variety of network samples from small-scale networks. So these samples represent what we could have in a controlled networking testbed at the vendor's lab. So particularly, these samples were from networks between 25 and 50 nodes. And then the solutions were tested in a dataset with samples from networks between 51 and 300 nodes. So these larger networks represent what we could find in real-world scenarios. So just to finish, what we wanted to evaluate is how these models scale from the small networks, and after training, test them in the larger networks. And we used as evaluation score the relative error produced on the delay predictions produced by the different solutions. Well, so after this quick overview of the problem, I would like to share with you some statistics after the end of the celebration of this challenge, and also a small discussion on opportunities for publications. So by the end of this edition, we had 130 participants registered, that they formed teams, in total 78 teams. These teams had participants from 23 different countries, and in general, we had a wide variety of profiles, including members particularly from the machine learning field, from the computer networks field, and also many members working at the intersection of both fields. And in general, we had very balanced profiles, including members from the industry and academia. So here you have a list of all the countries that were represented in the different teams registered. And well, I would also like to share with you that you will have opportunities for publications. So particularly the IT Journal on Future and Evolving Technologies has recently launched a special issue on AI/ML solutions in 5G and future networks. So this special issue is especially intended for participants of the ITU AI/ML in 5G challenge to submit papers describing their solutions. So I would like to encourage all of you to consider to submit a paper here with your solutions. And the main date here for you would be the paper submission deadline, which is by the end of January, so particularly the 31st of January 2022. So you can just start preparing your papers if you're interested. Well, just let you know that this is a recent journal, but it's gaining much attention. So the editor-in-chief is Professor Ian Achilles, which is very well known in the community of computer networks. He's a great researcher with an H index of 131. Well, if you have any questions about this special issue, you can just drop me an email or write through the chat, please. So just let me know, and we can discuss about this. Okay, so after this, we will proceed to the announcement of the awards, and this will be done by Albert Cabellos, who is the director of the Barcelona Neural Networking Center. So please.
Thanks for the nice introduction and explaining the challenge very well. So I'm not going to spend that much time. I would like to congratulate all the participants and specifically all the winners of the challenge. I think that this was a very competitive challenge. First of all, because we always work a lot and do our best to propose challenges that are well beyond the state of the art, meaning that you guys manage to propose a solution that it is not written on a paper, right? You need to come up with a new idea because the challenge is designed to go beyond the state of the art. So as Tebo was saying, you are the winners of a very well participated challenge with 130 participants, 78 teams, 23 countries. And this is actually the most participated challenge, and I believe that it is the most participated GNN challenge across the 2 editions. And I believe it's the most participated challenge across all I2T challenges. And even that this is a very competitive challenge, you manage to achieve outstanding performance, because as you will see, you achieve an accuracy which is very good, and we were very surprised about that and very happy about that. Also, the ranking of the solutions is extremely tight. So as I was saying, right, you are a winner of a very competitive challenge. And without any further ado, I'm going to announce the winners. I will ask everyone, if you want, to unmute yourself and to turn on your camera, so to make this a little bit more human, let's say. And I'm going to announce the winner. So Pepe, next slide. Okay, so I'm going to announce them from the 5th to the 1st. Okay, so fifth winner is Team Gain. Participants are Miquel Ferreras, Paola Soto, Luis Fábregas, Pere Vilà from Universitat de Girona and University of Antwerp. Congratulations. I'm not
Thank you so much.
I'm not hearing people clap. Do you want to say something, Michael?
Well, thank you. We didn't expect to have to stay in the top 5 classification, so we are glad to be here. And well, it was our first time working with graph neural network, so we are pretty happy with the result.
Congratulations. Okay, so the fourth is Team Eric Re with Yifei Jin, Pedro Batista, Alessandro Prevetti, and Marius Dautuis from KTH in Sweden and Ericsson Research. So congratulations.
Thank you for organizing this. It's such for me such a proud, and I'm feeling very much recognized at this place. But I'm still trying to learn this community, and wish I could do more, or let's say contribute more in this research area, as much as proceed with my research.
It's our honor, honestly. Thanks. So let's move to the third. The third award goes to ZTE AI Ops, Wang Zuyao, Tan Yongsheng, Gao Yong, and Tan King Kung from ZTE Corporation.
Thank you very much. Thank you.
Congratulations.
Thank you very much. Okay, thank you.
Yeah,
Can you hear me?
Yeah, we can hear you. Congratulations.
Okay. I'm glad you announced this result, and in this game we learn a lot and have a lot of fun. And yes, thank you all the organization for these games, and yeah, happy for everyone.
Thanks, Hui. Thanks. It's an honor to have you participating here. Okay, so the second in the ranking is SoftGNN, Charles Bourdeau, Hui Duong, Brigitte Jomard, and Junior Momo from Concordia University in Canada.
Thank you.
From Team SoftGNN.
Mm-hmm. Yes, hello. I'm presenting for Team SoftGNN. I thank you very much for organizing this competition. We thought it was very interesting, and obviously second place is a pretty nice prize. So, yeah, thank you very much to the organization team once again. And well,
congratulations for the second position. Okay, and finally, the winner of the challenge is Team Parana, Bruno Klaus from Federal University of Sao Paulo. Bruno, congratulations.
Yeah,
it was a very tight competition, I will show you that later. Congratulations, Bruno.
Yeah, I know it was really tough, really tight competition. A lot of work to climb up the ranks over the course of over the duration of this competition. So thanks to you guys for organizing this competition. It's really good to actually be at the forefront of those sorts of graph neural networking challenges. I feel that there's not enough of these challenges with graph neural networks at the moment. So that is really good. And also thanks to all the competitors that made it really tough and worked really hard.
Yeah, congratulations, Bruno. It's very well deserved award. So, that's important for you to know also. The top 3 solutions will be considered for the I2T Grand Challenge Final, where there are some cash prizes. So the date for this is December 14, where the Grand Challenge Final will be celebrated. There is no action required from you at this point. We will contact you shortly regarding the details and what you will need to do to participate in this Grand Challenge Final. Okay. So this is the, as I was saying, yeah, next slide, please. Yeah, this is the final rankings. Just to give you an idea, our baseline had 300% of MAPE, and the winners are in less than 2% of the MAPE, right? So it's an extremely tight competition. congratulations to all of you. We are also very honored to have you participating here and to propose those outstanding, surprising, inspiring solutions. And finally, I would like to join Pepe when he was, because we like to thank I2T for organizing this challenge, for providing all the support, for being so professional, for being so encouraging. I believe that this is a great success because of you, and in particular, Thomas, Vishnu, and Reinhard. I believe that Thomas is here. I think I saw you later on. Thomas, if you want to say something.
Okay, thank you so much. I do appreciate the work that you are doing, guys, here in Barcelona Neural Network. I think working together 2 years, and we see groundbreaking solutions. And we had some publications from last year. And this year also, we can see that from the baseline, you can see teams like having very good solutions, less than 2% of them have the excellent results. So we hope that these results will be translated to some research work, more groundbreaking solutions for graph neural networks, as well as publications in the ITV journal. So thank you so much and good luck.
Thanks, Thomas. Thanks. Okay, so that's all from my side. Now we will hear for the participants how they will present their solution. We ask participants to keep your presentation on time and to be very strict with that, which I believe it's 8 minutes per presentation. And I also encourage participants to ask as many questions as you want, because those are outstanding solutions, and we are very curious about how you manage to reach this kind of performance.
Okay, just let me say some words. So, well, thank you for all your comments, and congratulations to all the teams that participated in this ranking. So for this second part, we prepared, or well, top 5 teams will present their solutions, and they will do it in the order of the ranking. So the first presentation will be from Team Paraná, from Bruno Klaus, from the Federal University of Sao Paulo in Brazil. So I will stop sharing my screen.
And I'll
Bruno, please
start sharing mine.
The project.
Okay, whole screen. Right. So I guess you can see it already.
Yes,
okay.
But not in full screen.
And now it should be in full screen.
Yeah.
Yes.
Okay.
Perfect.
So once again, welcome. I'm Bruno Klaus from the Federal University of Sao Paulo, currently a PhD candidate and part of the Paraná, which is a research group which stands for Pattern Recognition and Network Analysis, coordinated by Dr. Dedan Berton. And today I'll be presenting the first place solution for the Graph Neural Networking Challenge. So let's talk about generalization on larger graphs. So there are a few approaches that we can use to predict the network delay. So we have the analytical approach based on queuing theory, which is pretty fast, but it also generalizes to larger graphs, but it doesn't have top-tier performance, even though it is based on good principles and can generalize. Then we have packet simulators, which has top-tier performance, but it just isn't fast enough, and thus it was prohibited in this sort of challenge. Then we have RootNet, which is the previous approach from Barcelona, and it is fast enough. It does have top-tier performance, but as you saw, over 300% error on when you try to generalize to larger graphs. So we have to overcome all of that. And to do that, we start by looking at the analytic solution, and we know that the analytical queuing theory baseline is able to generalize well to larger graphs. So we want features that are invariant with respect to graph size. And the baseline predictions is certainly that. So our main idea was to use graph neural networks to fine-tune the baseline prediction. And if we just take raw path and link features, we get bad generalization. If we get raw features and divide them by the average number of packets generated, for example, then we already get a little better generalization. But really, the main difference was using those sorts of baseline features for path and link level prediction, and that was able to get us the best generalization possible. So let us talk about model architecture and implementation. We implemented everything from scratch in PyTorch and also PyTorch geometric. So we also had to convert our input to the data class or to PyTorch files with the extension .pt. And we had two message passing models. First model, I wanted to just use all computational power, make it really big, and then it took way longer to train. But in the end, it didn't do much. With model 2, we get a way smaller model that achieved essentially the similar results. So when you are very worried about generalization to a distribution that isn't exactly the same, then maybe just making the model as big as possible, maybe you don't need that as much. So the final submission was just the average of both. So again, we had three types of entities, paths, links, and we also tried to include nodes at first, because that was something that we saw in the previous edition of this challenge. But then we realized it wasn't helping much. So the second model, we didn't use, for example, edge to node and path to node messages. We scrapped that. We also need to have fixed columns that contain the initial features, and also hidden state columns that are 0 initialized, and then they change over the course of the message passing iterations. Other architectural differences against RootNet is that we use graph convolutional gated recurrent unit for linked path message passing. We have to order links according to path traversal. Moreover, we also use graph attention convolutions for the rest of message passing. And also the most important thing really is that we use baseline features that are also kept unchanged during message passing rounds. Aside from that, we use multi-layer perceptrons before and after message passing. I think RootNet doesn't use before, just after. And also we use link level predictions. We actually predict the average utilization. And then from the average utilization, we get the delay on each link from other stuff that we know, such as queue size and link capacities. And lastly, we predict the path delay using the formula. Just sum up the delay on each link of the path. Okay, this is the big kind of algorithm, so no time to look at all that. But here you can see you have the number of message passing iterations, then paths receive messages using the recurrent unit, then links receive messages, then we concatenate, multi-layer perceptron, and then we just sum up to get a path delay. So main thing is that model 1 had a bigger number of input columns, 64 for paths, links, and nodes. Model 2 doesn't even have nodes, just have paths and links, and just 8, which is like if nothing, really, really small. And we also reduced the size of the multi-layer perceptron at the end. Slight variation on the number of baseline iterations as well. So you can see with minimal effort, really, you can just take the baseline prediction, just modify it a little bit, and you get something that is way more robust than we're just using those classic, those raw path and link features, which was a bit of a surprise that it worked so well, just using the baseline. So for results, not sure how much time I have left, but here it is. We separated with 3 validation sets. Each has a different characteristic. We didn't use all of that because they have larger networks, they take longer to evaluate. So we just took a few subsets of those validation sets. So the first model, it was 2 points. Wait, just hold on a second. The first model that we submitted was actually without this baseline, and we got something like 22.58% error, which was enough for around 5th place, I think, in the challenge. That was just dividing the features. Then when we actually incorporated the baseline, huge difference. Here you can see the 2 models. Model 1, validation 1, 2.7, model 2, 3.6. And then the model 2 was better for validation 2. It kind of inverts the situation. And then it's curious that in the test set, they actually are pretty much identical, but one was a little better with validation 1, the other for the second validation set. Then when we have 2 models that are kind of different, but they attain the same sort of result, when you take the average of them, usually you see some sort of improvement, and that was what we saw here. So we got a 1.27, which was good enough for first. I actually wanted to just use variations on the second model because it was faster to use, but we had a little problem on the website, so I thought it was safer to just use the average of model 1 and model 2 at the end. And that's basically, okay, yeah, you have the kind of training curves. When you use model 2, it just goes, it decays really quickly for training set. And for validation set 1, it actually stays kind of constant throughout, but sort of low. And then validation 2 and 3, which is I forgot exactly what was the difference. One uses different sort of link capacities. The other just uses larger networks. But yeah, for validation sets 2 and 3, it takes a little bit longer to make everything go down, and make the error go down. I have to wait a little bit more. And that's it, really. Here are all the references, and that's it. Hope I didn't take too long. If you have any questions, you can tell me right now or just email me.
Okay, so thank you very much, Bruno. It was a really interesting presentation and a really interesting approach. So congratulations again for producing such interesting solution to the challenge. So now it's the turn for questions. So please, if there are any questions from the audience, you can directly unmute yourself and make them, or use the chat, whatever you prefer.
Hi, Bruno. Oh, I see someone else has a hands up.
Okay. Well, I think that Jean maybe
it's Fred.
Asked first,
if
so
you allow
please
me.
go ahead.
Thank you. I'm not going to take too much time. First, I was really impressed also by the presentation. And just about how did you get the intuitive idea of just doing a mean of two solutions?
Oh, it's just that I said sometimes I do kind of participate in other random data science challenges and the sort, and usually just taking two solutions, you expect them to be good. Usually when they are different from each other, if they have a different perspective, you get a really good gain from kind of just taking the average sort of prediction, the basic ensembling stuff. Well, especially when they are different from each other. This one was not so much different, but it was still different architecture. Then, yeah, I thought it would be a good idea to even then just take the average, and actually submitted that, I think with like 5 minutes left on the challenge or something. And it works really well. That was the main difference.
I think it's brilliant, actually. And just thinking, do you have also some intuition if there is a way to predict which one is the best, depending on some metric on the topology or on the demand or on something on the network that can tell you if model 1 or model 2 will give a better result?
Yeah. Of course, you saw in the test set, they were pretty similar. However, in the validation set, we did see that depending on the kind of problem that was being tackled, either model 1 was better or model 2 was better. So when you kind of have to see the difference between the training set and what you want to test on. And if it just have, I think, different link capacities, I think it was model 2 that was a little better. And then if not, I think it was model 1, something like that. So if you, in this kind of regard, you could try to use that kind of topology information. But they're both really pretty similar, pretty good, I think.
Well, thank you very much for sharing your experience.
Okay, thank you. So maybe Jordi, can you go ahead?
Well, it was actually kind of the same line. No? I just wanted to ask. So it's actually a regular average, nothing, so just take the two outputs and divide by 2.
Yeah, no sort of weighting or whatever, just the simple average, because it's kind of hard. It's you can't, because if you do anything more than that, you're kind of tuning way too much, I think. I just think, okay, one and the other, that's it. You know, especially because I had only one shot as well, because we had some stuff in the last day.
Okay, yeah, great. Very interesting. Thanks.
Okay, thank you. So I don't know if I'm respecting the order, sorry for that, but maybe Paula, can you make your question?
Yes, hi, can you hear me?
Yeah, I can hear you just fine.
Okay, I would like, because you talk really fast, and I would like you to talk about a little bit more about the architecture of your models. So you have two models, right? The architecture of your models are more or less the same, so you use several layers, as I understand.
Yeah, it's loosely inspired by the RootNet approach from the previous approach from Barcelona, but the main difference between the two models, aside from the sizes of the hidden layers and stuff, is that it's not shown here, but model one, we actually tried to model the nodes explicitly, so we had messages actually going to nodes and from nodes as well, as they were sort of a separate entity. And whereas in model 2, we just look, okay, so nodes don't actually have any distinguishing features in this data set. If they had, maybe it would be worth it, but they don't, so maybe just scratch that and then just use the just paths and links, and it proved to be enough.
So basically, it is an inspiration, or you got inspired. This architecture is like a modification of the route nets, or
well,
how did you get to the architecture, to the final architecture?
Yeah, for sure. I looked at the RootNet, but I do know that there are some differences. Choices of convolution, for example, was for graph attention instead of whatever they used there, and I don't know. It's more generally an example of message passing sort of solution. Maybe even the authors of RootNets that are here will be able to tell how much similar it is and how much it isn't. Maybe it's just similar to a more general thing, or more similar to RootNet. But of course, I did look at RootNet. It was inspiration. It was listed at the Challenger website, so of course that was kind of the first thing I looked for. Also had to learn a lot of queuing theory because I didn't know pretty much anything for the challenge. Yeah. I hope that answered sort of your question.
That's great, really complete solution. Well, so going to the next question, maybe Christoph, can you make your question?
Okay, thanks. So first of all, congrats on the nice result. And I go back to the question regarding averaging. This is really interesting approach, because the average of two models is kind of a meta model. So I'm curious if you considered this, or even tried training end-to-end ensemble of two models where the final output is the average of two, and just it worked.
Yeah, it's an interesting question. We could just put the model 1 here, put the model 2 here, concatenate them, and then just try to train that to make a final prediction. But model 1 just took way longer to train than model 2. In the end, I thought that model 2 was the better of two models because it was way faster. And I wanted to actually maybe train model 2 times model 2, maybe side by side. That could even be enough. Model 1, I thought it's good, but I think it had a lot of fluff that didn't need to be there. I'll probably have to make some more experiments. I think it would be just a little bit imbalanced. You have kind of a big model on one side and then a little small model on the other. But yeah, it warrants more experiments with that for sure.
Okay, thanks for clarification.
Okay, so Albert, please.
Yeah, actually, I'm a proxy of two questions that are written on the chat. So the first one is from Sergio Badal. He's asking, in which machine did you use for training? Meaning that it was a very powerful machine with GPU, lots of RAM, or rather a smaller machine?
Oh, it's the one I have here, which it's actually pretty beefy. the RTX 3080, but the first model, I wanted to make it as big as possible to get the best results. And then I realized as the second model, you don't need pretty much any of that. I'll need to get back on the actual utilization for the second model, which is like way less. It's nowhere near the amount of VRAM that is available, for example. I probably have to look at actually how much RAM it used, but it really not much. It had way more computing resources than it needed.
Yeah, and then Carolina Alvarez, she's asking, and actually that's exactly my question. If you could quickly summarize how you use the baseline or elaborate on that.
Yeah, so I got the idea first for the baseline because in the root.net paper, they do mention the baseline and they list equations with the sort of lambdas. Okay, so here you have this, then you kind of have a fixed point algorithm or whatever, you can derive the solution. But I couldn't find the actual algorithm exactly. So I pretty much had to implement it on my own and kind of figure it out how it works. And then I eventually got it working. And I got the more or less the same results that he got in the other set, which I think the training set they used for that paper was a little bit different, but it was pretty much the same results that I got using the baseline. Okay, so I calculate the baseline. It's pretty fast, because it doesn't need a lot of calculations, just one or two, I think 3 or 4 iterations or something. Then we just use the baseline as it was a kind of a link feature or a path feature like the other features. And then you just keep them, you preserve them during message passing iterations as you would for the other sort of features.
Okay,
so there's not much to it. I think it's pretty straightforward.
Okay, so thank you very much, Bruno, again. I think we can continue with the next presentation.
We have Carlos that he raised the hand. Maybe that should be the last question.
Ah, okay, sorry, I didn't see it.
Yeah, sorry. Well, first of all, congratulations. And my question was a bit related about the meta model. Do you think that if you try to train more versions of the models with a different size and like different topologies and number of nodes, do you think you could improve upon your solution?
Yeah, I think I can. You could fine tune it further. I mean, for example, if you even have a few networks that are larger instead of a huge number, you can already use that to maybe you can actually train, for example, a convex combination of those models. That is something that you see, for example, in most sorts of competitions. But I didn't want to use explicitly any sort of validation set or anything. So, but if you want to use, you could use just a portion of it, because this sort of convex combination, you don't need much data to actually fine tune. You could just, that is one way you could improve that, for example.
Thanks.
Okay, so thank you very much. I think we can continue then with the next presentation. Thank you, Bruno. Now the second presentation will be from the SoftGNN team. It will be presented by Charles Boudreau from Concordia University in Canada. So please.
Let me just share my screen.
Okay.
Okay, and done. Whoops, sorry. Let's see. Let me just change it. There we go. All right. Okay. So hello everyone. My name is Charles Boudreau. I'm representing the SoftGNN team for the presentation of the results for the Graph Neural Networking Challenge 2021. And I'm currently a PhD student under the supervision of Dr. Brigitte Jomar, who unfortunately could not make it to this presentation today. And with that, let's get started. So our solution was essentially we were working from the RouteNet implementation provided by the competition organizers. And we were mostly working on trying to improve the results of the RouteNet through changing the feature design and as well as the types of outputs. for this we have we had a few different directions that we went to in order to try to improve RouteNet. Here on this slide, you can see all of the elements are things that we tried in the model, and the highlighted elements are the elements that we kept in our final configuration. In order to address the out of distribution data, we originally conceived a data augmentation scheme, which did have some positive results, but the increase in training time that it led to meant we dropped it in the end. If we had to select two elements that we added to the model that had the most impact, we would say it would be in the feature design, this link load feature, which I will cover shortly, as well as changing the prediction from, instead of predicting direct delay, we predict the link occupancy and infer the delay through the formula provided by the organizers. With that, we move on to just the general overview of the solution. So in the end, for our final predictions, we had an ensemble method of two that ensembled the results of two models based off RouteNet. So the two RouteNets have also effectively have the same hyperparameters, but they only differ in terms of input features that we added, with the second model having one more, and which one I will get to. So estimate so they predict the queue occupancy used to estimate the delay for the flows, and then we simply average them together to get the final prediction. Moving on to the inputs. So here we have the inputs for the RouteNet model that we use. So for the flow features, we kept the traffic, which is the average bandwidth of the flow, the average number of packets of the flow, and the EQ lambda, which is the average bit rate of the distribution generated flow. And for the link features, as you'll notice, instead in the base RouteNet implementation, they have the raw capacity or link bandwidth as a feature. We've elected to replace this with something we call link load, which is essentially a relative feature that takes the sum of all the traffic of all the flows that go through a given link and divided by the capacity of the link. We found that replacing the raw capacity with this link load feature has a pretty large positive effect on the accuracy of the model. Possible cause for this is that this feature is probably more relevant to the prediction of the delay. And while RouteNet may have access to all the raw data in order to infer this relation, as the neighboring nodes would have all the traffic values for the ones going through this link, but it might not be able to infer this relation or something of the sort. We also tried near the end of the competition raising it to the second and third power, and we found it had possibly a modest effect on the accuracy. Possible reasons for that is that it might help further differentiate the heavily used links from the lightly used ones. And another one is that it was mentioned that GNNs and most neural networks have trouble generalizing, extrapolating to unseen data, as in they can only fit linear functions. One way to get around this would be possibly to encode nonlinearities into the features themselves. So essentially, we tried that along these lines. We found a small benefit to it. Next, in order to address the issue of out-of-distribution data, the competition organizers proposed to predict, instead of directly predicting the delay, predict the queue occupancy of the outgoing queue for the link, and then inferring the delay from the given formula. So here you have the predicted value, the queue occupancy, multiplied by the size of the queue in the number of packets, multiplied by the average packet size, and then divided by the capacity bits to get to the delay for the individual links. Then the delay for the individual flows is essentially the sum of the link delays for the links that compose the flow. So this table is a quick summary of what the changes we made to the model during the course of the competition. If you'll see here, the two changes that we thought had the largest effect, according to this, would be the addition of the replacing of capacity with link load, as well as predicting queue occupancy and inferring delay instead of direct delay prediction. Past that, we've just made small tweaks to the model, like essentially we changed the hyperparameters to make it bigger. We also changed the way we calculate the average packet size in the past the formula, where before we used the average of the distribution, which was 1,000, but then we essentially changed it to one for 80 individual links instead. So here's just a quick set of the final hyperparameters for both models in our ensemble. Both share this, so these are essentially essentially bigger than the baseline implementation. We also added an extra layer on readout, more message passing rounds, but otherwise no change, unchanged. Here's a diagram of the final model, where this is essentially just a diagram of route nets. So there were no significant changes to the architecture. Essentially, it was mostly hyperparameters that changed. And that's about it for the presentation of our solution. In the future, we'd like to see if how far the scaling goes, because right now we have fairly decent performance on scaling up to topologies of 300 nodes, and we're wondering if it can go even higher, 500 or 1,000 nodes. And we're wondering also if it can be leveraged for different key performance indicators, such as packet loss and jitter. So once again, I'd like to thank the organizers for organizing this competition. I felt it was very interesting, and we would be interesting in seeing in collaborating further in the future. Thank you.
Yeah. Great, thank you very much, Charles. I think that it is a really interesting approach. So it's interesting also your lines for future work. So it would be good for all of us, I think, to contribute to this area. So are there any questions from the audience?
I have a question, actually. Charles, thanks for your presentation. My question is, so I found it very appealing and very interesting, the data augmentation. And I have two questions. So the first one is, if you could elaborate a little bit more on that, on data augmentation. And the second one is, although this is a very popular technique on convolutional neural networks, and in particular for computer vision, I have never seen that done for graph neural networks, but maybe it's because I didn't find the right paper. I don't know if this is a new thing or it's a common thing also in GNNs. So that's my two questions.
No, our approach for data augmentation we started at the beginning was essentially so since we have here the relation of how the capacity, how the delay is influenced by, say, the capacity and the number of links, then essentially what we did is that we added so we took the existing example and essentially just added more nodes and modified the delay values in consequence. So essentially, in consequence, in accordance with this. So the approach to data augmentation is very problem specific in this case. We ended up dropping it because we essentially because it was essentially making some very large training on very large graphs. So it was increasing our training time to quite a bit. And while it was having an effect, because it was having a positive effect, because the baseline was about 308, if you'll recall. When we implemented the scheme, it drops the make to, so we essentially tried to, so we essentially drops the make to about 50, because we're essentially trying to change the, we're essentially applying a transformation to the training set to make it resemble the validation set, the different validation sets. But it increases the training time to a fairly long, so we ended up dropping it in the end.
Okay, thanks.
Okay, thank you very much. I think there are no more questions. So I would like to make a quick question. So just, I saw that you use the quadratic and cubic values of features.
Yes.
So could you elaborate more on this? So what's the rationale behind this? I think it's a really interesting approach, and I would like to know more about this. Thank you.
So there were two general lines for why we tried this near the end of the competition. The first one is that if the values are very close together, depending on the range of the values, then raising them to second and third power might set them apart and provide more differentiation, which a model might be able to pick up on. And second of all, I've sourced it in one of the papers that I've read by by a Shu here about neural network extrapolation. It covers how neural net works, GNNs, as well as regular fully connected networks extrapolate or try to fit data that is outside their training distribution. What they mention in here is that whenever a neural network is given data that is within its training support, then it can fit any type of function. However, when it's given data that is outside of the distribution used to train it, then it only starts fitting linear functions. And I think in their paper, one way to get around this is that they sort of encode nonlinearities into the feature design. And I think especially for GNNs, it allows the model to extrapolate better. Now, in their case, in their specific example that they use in their paper, they know the function that they're trying to fit when they try to train the network to find. But in our case, we're essentially just trying things. But near the end, when we did add it, it did give us shave us a few fractions of percentage points. So I guess if it works, then it might be because of the reasons listed here.
Okay. Thank you very much for the answer. Well, I think that we are a bit running out of time, so I would kindly ask you to use the chat for further questions. Let's try to make the following presentations on a schedule. Sorry for that. So the next presentation will be from the third team, the ZTE AI Ops team, and the presenter will be Jing Jifei. So please, Jing, could you start your presentation? Thank you.
Okay. Hello everyone. I'm Huangzhuo Yao from ZTE AI Ops teams, and I'm happy here to share our solution to everyone. Our solution is based on the RuNet TensorFlow entrainment provided by the BNN, and we try to predict the queue utilization and infer the path delayed with a simple poster process, as the guideline suggests. This is shown below here, and here our modification made to the RuNet may be simple. We replace the embed layer for the path and links states with a field states with a vector directory with a path and link feature and zeros. So that means we just remove the embedding layer and put the original feature there. And the second is we train the neural net model on the predicting the queue utilization, and load the weights on another neural net model, which with the post-processing and then predicting the path delay. So we just write two model function and one for the training, and then load the weights to another one and do the prediction. Here is the training mode and predicting mode. And the training mode, we output is the link occupation, and in the predicting mode, and we output is the delayed. Here is our hyperparameter. We put the link state diameter to 512, and it's the same as the path state. And we made the message passing turns to just 4 times, and the real units is 640. So there's large numbers, and we start the learning rate and 0.001 or 0.001, and we manually reducing the learning rate when the NAP reducing very slow at the training. Where we did 1/2 on the epoch 32, and we don't use the layer 2 regularization in the first input layer on the readout, and we just use the one L2 regulation layer there, and we use the GPU GV100GL for the training, and the training time is about 6 and 7 hours. Thank you.
Okay, I guess you can see my slides. So, well, this is the last part. We have to say goodbye or see you later if it would be much better. So just before finishing, I would like to summarize a bit the results. So here you can see again the final ranking. And in general, I have to say that we have seen really, really impressive results in this edition. So honestly, we didn't expect so good results. And particularly, we could see that the top participants that have presented here have completely solved the challenge. So just as a reference, the baseline solution that we gave, RoundNet, which somehow represented the state-of-the-art GNN models for this problem, had a score or a relative error around 300%, so more than 300%, and we saw really good solutions below 30% and 2%. So I think that they really solved the challenge. So congratulations to all of you. In general, to all the teams that participated here. And well, it's time to talk about the next step. So of course, as I told, this is an annual competition, and we are already working on the next edition for 2022. So it is expected to be celebrated from around the month of May, but we will give some news on our official media channels. So if you are interested on following on stay tuned for next editions, you can subscribe to the mailing list of the Graph Neural Networking Challenge, or follow the Barcelona Neural Networking on LinkedIn or Twitter. So, well, I will share the slides later with you. I think you also have the links in the chat. So, also you can follow the Slack channel of the IPU AIML in 5G challenge. So they will give also some updates about the next edition. So I think that Albert Cabellos, maybe you want to say some few words.
Yes, and then we close this session. So again, congratulations to all the participants. It was truly an honor to see your solutions and to see how groundbreaking they are. We will keep our open access policy, meaning that we will release all the data sets and we will point to your repositories if you also open source your solution. And I encourage you to participate in the next challenge, which I promise you that we're working on a problem that it's again beyond the state of the art. And with this, I believe that we can close the session. So thank you, everyone.